Hey, all, today we're going to continue talking about conditional probability. And we're going to add on to what we did in the last lesson. So in the last lesson, I showed you a formula for conditional probability um, that showed how we would calculate this piece of the equation. And so all this equation is a sort of algebraic manipulation to isolate the probability of event A and event B happening, which gives us our multiplication rule. So we can use this rule for independent and dependent events because it's really just saying, hey, let's multiply the probability of A times the probability of B, given that A has happened. And if the probability of B doesn't change with A happening, then we just plug in the probability of B. When our events are not independent, then we're going to need this conditional probability of event B happening. So let's look at an example. So you can pause and read through this if you want. I'll sort of briefly explain. We have a factory that produces two types of batteries, regular and rechargeable. And as does happen in factories, sometimes things turn out to be defective. And so they have found through their quality control that 1% of the rechargeable batteries are defective and 2% of the regular batteries are defective. They produce 75% of the batteries they produce are regular, 25% of them are rechargeable. So I'm going to do some documenting of percentages, or probabilities. So the probability any battery is rechargeable is 0.25. The probability that any battery is a regular battery is 0.75. Then we have some conditional probabilities because I'm told that 1% of my rechargeable batteries are defective. So the probability we have a defective battery given it's rechargeable is 0.01. The probability our battery is defective given that it is a regular battery is 0.02. And so what we want to find out is what is the probability that we get a regular battery and it's not defective? And I'm going to do two different probabilities. I'm going to do the probability we get a regular battery and it's defective first. It's my lesson. I'm allowed to change it. So the probability that we have a regular battery and it's defective, we would first take the probability it's regular, and I should write REG because we have two R's. And then we're going to multiply it by that conditional probability that our battery is defective given we know it's a regular battery. So we are doing 0.75 times 0.02, which gives us 0.015. So here we are using the multiplication rule with a conditional probability based on the condition that we know our battery is a regular battery. The original question was, what is the probability we have a regular battery and it works? So probability that we have a regular battery and it's not defective. I'm going to use the complement of being defective. Well, we use the probability of getting a regular battery. And then we have a conditional probability, even though it's not told to us. If 2% of them are defective, then that means 98% of them work. And so when we multiply those two together, we get 0.735. So that's the probability that we'd randomly select a regular battery that works. So again, using the multiplication rule. So now we want to know the probability that a battery chosen at random from a shipment turns out to be defective. Well, there are two possibilities for having a defective battery. We could have a regular battery that's defective, or we could have a rechargeable battery that's defective. So those are mutually exclusive events. You can't be a regular battery and a rechargeable battery. So we can find two probabilities and add them together using our addition rule because we have mutually exclusive events. So we can find the probability that we have a regular battery and it's defective, which we actually already know. And we'll add to that the probability we have a rechargeable battery and it's defective. So we already know this first piece. We just calculated that. It is 0.015. We can calculate this piece using the addition or the multiplication rule that we used the last time. So we would have the probability of a rechargeable battery, and I'm going to skip the notation here. The probability of a rechargeable battery is 0.25 because 25% of them are rechargeable. And then we said that 1% of them were defective. That's our conditional probability, the probability of being defective given it's rechargeable. And so we would get 0.0025. And then when we add those two together, we get 0.0175. This is the probability that we pull any battery off randomly off of our production line, and that battery is defective. So somewhere close to a 2% chance that our battery is defective. And so I've been using the formula, and I want to point out a way that we could use a tree diagram to sort of map out these scenarios if you need a visual. So we have batteries, and then some of them are regular batteries, and some of them are rechargeable. I'm going to write my probabilities on here. So 75% regular, 25% rechargeable. We have some batteries that are defective, that are regular, and some that are not. I'm going to call them D complement. So for our regular batteries, 2% are defective, making 98% working, 1% defective rechargeable, meaning 99% working. And then we can calculate the probabilities of each of these four options: a regular battery that doesn't work, a regular battery that does work, a rechargeable battery that doesn't work, a rechargeable battery that does work. And so we can calculate all of the and probabilities: regular and defective, regular and working, rechargeable and defective, rechargeable and working, by multiplying, which is what we did throughout this lesson to get these answers. And this, of course, is the only one I didn't do beforehand. And so what's nice about this sort of diagram is it has all the probabilities on it. It has the probability of being regular or rechargeable. It has all four of our conditional probabilities being defective given it's regular, working given it's regular, being defective given it's rechargeable, working given it's rechargeable, and then the combinations or the probabilities of each individual possibility. And so what we should get if we add all four of these probabilities up is we should get a value that is 1 or close to 1 if we have rounded, which I don't know if I rounded. I probably should have paused before I calculated, but here we are. If you add them all up, they add up to exactly 1. So there are 4 possibilities when I pull a battery off. These are the probabilities of each. They should all add up to 1. Probability always adds up to 1. So you're not required to use a tree diagram. It's not something you have to do when you do an example problem. It is just a tool that you can use if you want to. So as I said in class, I want you to do these problems on paper. You can access through them through Canvas if you don't want to stare at them through the video, and then bring your answers to me so I can go over them with you and we can fix any mistakes that you may have made if you did. As always, take your time on these. If you need any help at any point, please do ask, and good luck.